purpose of this talk, I'm going to talk about the history of the GIL, what problem existed out there, how the GIL solves it, the ramifications of the solution, how it's still affecting us today, and how it may change in the future. And the story starts in 1992. 1992, Python was only 2 years old. It was still a very young language. It was still changing rapidly. It had been released on the internet, but it was still mainly used at CWI, where Guido was working at the time. Now, there's this big new technology on the horizon that people were talking about. It was something that operating systems were going to do for you, and it was called threads. Threads, if you don't understand, they're kind of like processes where, let's say that you had a process and you were running, you're doing work. You could create a new process, and that could be doing work, but they didn't share any state. Threads were kind of like that, where you could have multiple processes, kind of, but they were sharing the same state. They were sharing the same process information, all the same global variables. In fact, SunOS already had support for them. It called them lightweight processes. The new operating system from Microsoft that was still in beta in 1992, it was called Windows NT, that had support for threads. Linux was going to support threads eventually, but it actually took a couple of years from this point. Now, back then in 1992, you didn't have computers that had multiple CPUs. You only had one CPU. So in order to run multiple threads at the same time, they weren't actually running at the same time. One would run, and then it would stop, and the next one would run. But it was clear that multi-core computers were going to happen eventually, and multi-threaded programs were exciting now. So everyone wanted to use threads. People wanted to use Python. People wanted to use Python with threads at the same time. But this wasn't going to simply work. You had to do some tinkering inside of Python in order to get threads to work properly. For example, Python had a bunch of global variables. Python in C, a global variable is kind of equivalent to a Python module attribute. So there's only one of them, and everybody can see it, unless you hide it, in which case it's local. But there's only one of them. If you had multiple threads and they were both trying to change a single module attribute at the same time, you might have a race and something terrible might happen. Same thing with the same thing with the C global. Also, Python used something called reference counting to manage the lifetime of objects, and believe me, I'm going to tell you all about it. So let's talk about what reference counting are, and then I'm going to show you how reference counting doesn't work properly, perhaps, under a multi-threaded environment. So here is the structure at the top of every object inside of the Python runtime. Every object that exists inside of Python has to start with these two fields. This is a C structure. It's kind of like a Python class. The second thing is the type of the object. That's a pointer to another class which has enormous amounts of information about the object. But this first thing is unsigned int obrefcount. That is a reference count of the object. A reference count is essentially the number of people who are interested in this object right now. So if there are 3 people who are all holding references to the object, then that reference count is going to be 3. And you have to manage the reference count. You have to add new references if you're a new person who's interested in the object, and once you're bored with the object and you're not interested anymore and you're releasing your interest in it, you have to drop the reference count. So there are these macros, incref and decref. Again, this is C code. This is kind of like a function call, except it's actually more like a textual substitution. So incref increments the reference count for you. Decref decrements the reference count for you. Decref is a little more complicated because there's a little code in there that says, let's subtract 1 from the reference count, and if the reference count is now 0, let's call delref, which is going to call your finalizers. It'll call dunderdel if it's an object that has dunderdel. And then it's going to release the memory, which is how we reclaim the memory, so that Python doesn't necessarily eat all of your memory in your computer, although Python's known for having bad habits in that way. Now, let's talk about what it looks like from the Python end. Here we have a very simple statement. A equals a new empty list. So we have a variable A, and it has a reference to this empty list that's floating out in the world somewhere. And the empty list has a reference count of 1. If we then say B equals A, we're creating a new variable called B and assigning it a reference, and the reference count has to go up to 2. Now, there's actually a way you can look at reference counts inside of CPython. There's a function call called sys.getRefCount. And if you pass in A, in this circumstance, you're going to get a value of 3. Now, why is it 3? Because A has a reference, B has a reference, and you create a new reference when you pass it into sys.getRefCount, which is only used as long as it's examining the object, and then it drops its reference count. So after sys.getRefCount exits, the reference count is going to drop back to 2 again. So that's how reference counting works, and that's fine. It's worked great in Python for decades. But if you want to add support for threads, you're going to have a problem. So let's take a look at what the problem might be. Let's say that we have two threads. I've conveniently named them thread 1 and thread 2. And they both have a reference to an object, and they're both going to run and do their work, and then they're both going to drop their references to this object. So both of them are going to call decref. In order to examine the problem, we're going to have to go a little deeper. So let's turn that into the C code that it turns into. But actually, even that is not deep enough. So brace yourselves. We're going to go into assembly language land. It's not terribly hard assembly language, so I'm just not going to worry about it. But let's say that object has a reference count of 3. And both of these threads are not going to drop their references to the object. So I'm going to go through this twice. The first time it's going to work, and the second time we're going to have this race condition and it's going to fail. So thread 1 comes along and says, load the reference count into AX. This is making a copy of a value, pulling it out of memory and storing it in AX, which is kind of like a variable inside of the CPU. So we have this variable in the CPU called AX, and we're setting it to 3, because we pulled the 3 out of the object, right? Now we're going to decrement AX. AX is now 2. And now we're going to store AX back into the object. So now the object has a reference count of 2. Working great so far. Thread 2 comes along, does the same thing. Load the reference count into AX, decrement it, store it back into the object. Object now has a reference count of 1. That worked. We had 2 threads that came along. The object had a reference count of 3. Both threads had reference to the object. They both dropped them, and the resulting reference count is 1. Worked fine. Let's do it again, but this time it's going to fail. And all we need to do in order to make it fail is execute these statements in a slightly different order. This is what we call race condition. So the first thread comes along and says, let's load the reference counter to AX. Boom, AX is now 3. Thread 2 does it at almost the same time. And the thread 2 now has an AX is also set to 3. Thread 1 says, let's decrement. So does thread 2. Thread 1 says, let's store AX. So does thread 2. The problem now, 2 threads have come along. It had a reference count of 3 to start. Both of them drop their references, and the resulting reference count is 2. This is a bug. The reference count is now 1 too high, and it is permanently 1 too high forever. This object will now live forever. Once the last person drops their reference count on the object, the resulting reference count will be 1. It's never going to reach 0. It's never going to finalize its call. It's never going to have its memory freed. So this is now leaked memory. This is bad. It's not as terrible, however, as the opposite problem. If you have a race condition around incref, then the resulting reference count could be too low. And if the reference count is too low, then you have a problem when people eventually free their reference counts. One person frees it, and it should have dropped from 2 to 1. Instead, it drops from 1 to 0. And now the object is finalized as a called, and it's free. The memory is freed. But somebody else still has a reference to it. And they try and use the object. At best, you crash immediately, and at worst, you compute erroneous results, and all sorts of terrible things can happen. So we need to solve this problem, this race condition, in Python if we're going to support threading. So what do? Well, you would add something called a lock. A lock is an object that only allows one person to hold it at a time. So we talk about holding a lock. So a lock is a thing that only one person can hold, and you establish a rule. You say, in order to talk to this thing, you have to be holding the lock. So 2 people grab it. One person grabs it successfully. They're allowed to talk to the thing. And the other person is trying to grab it, and they have to wait until the first person releases it, and then they can talk to the thing. So you might add 1 lock per global variable and lock everything, have 1 lock in order to talk to this, and then another lock to talk to that. Or you might group them together a little bit. You might add reference counts just for 1 reference count for all, 1 lock for all reference counts, or multiple locks for reference counts, sort of splitting them up into bins. But all of these approaches can result in what's called a deadlock. Well, let's talk about that. So this, again, is a classic thing from multi-threaded programming. Let's say that we have 2 threads, thread 1 and thread 2. We have 2 locks, lock A and lock B. Both of these threads want to interact with these locks, but they happen to interact with them in opposite order. So thread 1 attempts to grab lock A and then attempts to grab lock B. Thread 2 attempts to grab lock B and then lock A in the opposite order. And again, I'm just going to go through the race condition here. Let's say that thread 1 acquires lock A. Nobody's holding lock A right now. Grabs it, it's fine. Thread 2 attempts to acquire lock B, grabs lock B, nobody's holding it. So now it's holding it, that's fine. Thread 1 comes along and says, let's acquire lock B. It can't because it's already held by another thread. Thread 2 comes along and says, let's acquire lock A, attempts to grab it. It can't because somebody is holding it already. These 2 threads are not deadlocked. They can never make forward progress. And this is a very common problem in multi-threaded programming. It results when you have multiple locks and people acquire them in the opposite order. And it's just inevitable. As soon as you have this problem, you're going to have the deadlocking problem in your multi-threaded program. So Guido did something that I would say is pretty clever. He added something he called the global interpreter lock, or the GIL. Almost 2 years to the day that the Python repo was created, the GIL was added. This is the check-in number 923 from August 4th, 1992. And this is the really salient bit. This is the global interpreter lock. It's a type lock, which is something that he added to make it cross-platform. It's static, so there's only one of them, and it's kind of hidden from the world, and it's called interpreter lock. It doesn't have the word global in it, but it is the global interpreter lock. And if you want to see what it looks like today, that's it. This is the GIL as it exists in Python 2.7. It's a little different in 3 now, because I'm going to talk about that in a minute. But we added a comment to say, this is the GIL, you found it. And we changed the type of it just a little bit so that it had this pythread in front, because we added this new thread library. Now, the rule in Python is, there is one lock, and it's called the GIL, and you have to be holding it in order to interact with the CPython interpreter in any way. If you want to run bytecode, if you want to allocate memory, if you want to call basically any C API call, you have to be holding a GIL. This is a really simple rule, really easy to get right. So actually, let's talk about the ramifications of this design decision. So again, it's very simple, which means it was easy to get right. It's very popular in the early days of Python to write extensions for things because there were a lot of C libraries that did a lot of really neat things. People wanted to call those C libraries from Python, and the easy thing was just write an extension module. The extension module rules were very clear, very easy to get right. And as a result, people wrote loads of extension modules, which made Python more popular. I would say that the design decision of the GIL is one of the things that made Python as popular as it is today. So I don't agree with people who say the GIL is terrible, it should never have been added. No, absolutely not. The GIL, part of the reason that Python is successful is because it had the GIL. Now, because there's only one lock, obviously you can't have deadlocks. I mean, you could add a second lock to your program and you could deadlock yes, yes, yes. But in terms of the C API for Python, it's impossible to lock because there's impossible to deadlock because there is only one lock. Now, this has ramifications for your programs. The classic thing is we talk about IO-bound versus CPU-bound programs, and I'm going to go into those in some detail. An IO-bound program, in effect, is a program that spends most of its time waiting for IO to happen. Like it's waiting to write to a socket, or waiting to write to a file, or read from a file, or read from a socket, or talk to the screen. It's waiting. And if you have a program that spends most of the time waiting for IO, then under the GIL, your multi-threaded program will work just great. And I'll show you why that is in a minute. But if you're a CPU-bound program, which is to say you have multiple threads that all want to be computing something, well, if you want to compute something, you have to be holding a GIL because you have to hold the GIL in order to run bytecode. So if you have 3 threads that are all CPU-bound, that all want to be computing something, only one of them can be using the Python interpreter at a time. So your program effectively becomes single-threaded. This is the sore point about the GIL. This is what everybody talks about. So let's explore a little bit more about how the GIL gets shared around when you're talking about IO-bound code. So there are some macros that are provided for C programmers that write extensions called py-begin allow threads and py-end allow threads. Again, these are macros. These are like function calls. They're hiding a whole bunch of code inside. And the idea is py-begin allow threads, that's allowing other threads to run. This is releasing the GIL. Py-end allow threads, that's reacquiring the GIL. That's saying, okay, somebody else has it, I'm going to wait, and once it's available, I'm going to grab it, and now I'm holding the GIL, and I can proceed and start talking to the CPython interpreter again. In the middle, you're not allowed to talk to the CPython interpreter, but that's a good time to go off and do some computation that's going to take a long time, like if you're computing some elaborate mathematical result, and it was going to take a long time, and you didn't need to talk to any Python objects, you didn't need to change any reference counts. It would be a good idea to drop the GIL in between. So some examples of places where you might drop the GIL. You might sleep. If you're sleeping for a couple of seconds, no, you don't have to hold the GIL, and you can allow other threads to run. If you're going to write to a file, or again, read from a file, that's a good time to drop the GIL. If you're going to read or write from a socket, that's also a good time to drop the GIL. And Python extensions and the Python library are very good about dropping the GIL when they don't need it. So this is what allows multi-threaded IO-bound programs to run successfully. But sharing the GIL in CPU-bound code just doesn't work. Because again, only one thread can hold the GIL at a time, so only one thread can run bytecode at a time, so everybody else has to wait, so your program has effectively degraded to a single threaded program. Now that's how it's supposed to work, but actually it didn't even work all that well. There's a researcher, a Python enthusiast named David Beasley, and in 2009, he did some research, and he published his results as a Chicago area Python user group talk called Understanding the Python GIL. And he showed that CPU-bound multi-threaded code could run slower than if you had just made it a single thread in the first place. It could get slower if you had multiple cores. And he also showed that CPU-bound threads could starve IO-bound threads. These are all terrible things. So for example, here's one of the diagrams from his talk. So there's this idea inside of Python. Let's talk about it. It's called sys.getCheckInterval. I surely put it on the slides. Sys.setCheckInterval and sys.getCheckInterval. This check interval, this is a number that is setting how fine-grained you're supposed to swap off between threads if they're running Python bytecode. So if you have a code that wants to run and compute things inside of Python, you're really supposed to release the GIL now and then and give somebody else a chance to run. And so we enforce this inside of CPython with this check interval, which is the number of bytecode instructions you're supposed to run before you have to stop and give somebody else a chance to run. And it's set to 100 in Python 2.7. So you're supposed to run for 100 instructions and then release the GIL and let somebody else run, and they can run for 100 instructions, and then maybe you can grab it again and you can run for 100. What this diagram is showing us is the number is not 100. This one in particular, so the top is thread 1, the bottom is thread 2. Red means I want to run, but I can't because somebody else has the GIL. Green means I'm holding the GIL and I'm running right now. And the x dimension is time. And you can see we've identified this one interval as 66,700 ticks. This is 667 times longer than it should have been allowed to run. So something terrible is going on here. But the terribleness doesn't end there. Let's talk about if we have two threads, and one of them is I/O bound, and the other one is CPU bound. Now, this is a classic computer scheduling concept. If you have an I/O bound task, it tends to run for a little while, just like a tiny little bit, and then it's going to wait on something really slow, like writing to the disk or writing to a socket. It's going to be sleeping for a long time. So if you have one I/O bound thread and one CPU bound thread, the CPU bound thread is never happy. It always wants to run. It's going to run as long as you will give it time to run. So what you want to do in a scheduler is you want this to prefer the I/O bound thread. You can keep it happy by just giving it a tiny little bit of CPU. This one will never be happy anyway, so you might as well make at least one of them happy. So in scheduling, you prefer to run I/O bound threads over CPU bound threads. What's happening in Python? The opposite. Thread 1 is I/O bound. White means I don't care, I'm waiting. Red means I am waiting to get the GIL. And then you can't even see the green where it's holding a GIL and doing its work and dropping it again. But thread 2 is CPU bound, and it's just holding a GIL and running forever and ever and ever and ever. And it doesn't give back the GIL. It doesn't allow thread 1 to run. What's going on here? So this is what was going on here. Inside the Python interpreter, this is the code that was supposed to release the GIL and then get it back later and let other threads have a chance to run. So if the interpreter lock is set, if we're running in multi-threaded mode, then there's this call here. It says pythread release lock. This is the thing that releases the GIL. So the idea is give another thread a chance. We have that comment up the top. We release the GIL. We have this comment that says other threads may run now. And then we say pythread acquire lock. We're going to reacquire the GIL and run again. So the fundamental problem with this code is there's no code here. There's nothing that happens here. This happens, and then mere nanoseconds later, this happens. So what happens is, we're going to let other threads run? Okay, release the GIL, reacquire the GIL. Release the GIL or reacquire the GIL. The other threads never get a chance. So that 66,700 ticks later, the other thread was trying to grab it the whole time, but we were holding it. We would release it and then reacquire it, release it and reacquire it. It just was, every so often, they would happen to win the race and grab the GIL away from us, and that was what allowed them to run in the first place. So this was kind of a dumb design, looking back on it. It wasn't really working at all. So in 3.2, a guy named Antoine Petrou added something called the new GIL. This was done in 2009 in Python 3.2. And what it is, it added a single new variable and then some mechanisms around it. This thing called GIL drop request. This is a flag that says, hey, somebody else is waiting. The next time you drop and reacquire the GIL, you have to make sure that the other person gets to run before you get to reacquire the GIL. And we added this, and most of the really bad behavior went away. David Beasley says he can still torture the GIL and get it to behave really badly, but it's a lot harder to do now. So this is working pretty well. So fixing it any further than this, fixing the crazy behavior that David Beasley can still do, would require even more elaborate machining around it. And at this point, we're talking about scheduling theory. And computer scientists have been working on schedulers for decades, and we still don't have a really good one. I think it's kind of a fool's errand to try and make it any more elaborate than it already is. I think the new GIL is good enough. We should just leave it alone, which is what we've been doing. So meanwhile, the world has kind of changed around us. As I said, Python was invented in 1990, and the GIL was added in 1992. And back then, all of our computers were single core, more or less. But something happened. In 2005, the CPU, so you really didn't see multi-core computers because you had to buy 2 different CPUs and you had to get a special motherboard that supported both of them. I did that in the 90s, but I was kind of a weirdo. Most people didn't have that until about 2005. 2005 is when the single core, the single CPU, would actually have multiple cores on it. So server CPUs and desktop CPUs and game console CPUs all actually became multi-core in 2005. 2007, laptops went multi-core. 2011, the CPUs used in tablets and phones and actually embedded systems on a chip all went multi-core. In 2013, eyeglasses went multi-core. In 2014, wristwatches went multi-core. Ladies and gentlemen, we live in a multi-core world now. And Python is kind of ill-appraised to take advantage of it because, as I say, if you have multiple threads that are all CPU-bound, you're in a world of hurt. Now, it's not that Guido hasn't heard about this, but in 2007, Guido wrote a blog post on his old Artima blog where he addressed getting rid of the GIL. People have been talking about it for, at this point, decades. And what he said was, I'd welcome a set of patches into Py3K. This is back before it was called Python 3 officially, so Python 3000 back then. I'd welcome a set of patches into Py3K only if the performance for a single-threaded program and for a multi-threaded but I/O-bound program does not decrease. This is a very difficult bar to reach, and in fact, this was more than 8 years ago now, and nobody has been able to meet it. So I don't know if we're ever going to meet this bar. I think maybe we're going to have to change our standards a little bit. So there have been some attempts in the past to get rid of the GIL. The first one that I know about anyway was called the free threading patch. This was written against Python 1.4. What it did is it didn't require any changes to the C API, so it didn't technically break any of the C extensions, at least not from the API level. What it did is it took all of those global variables and put them as structure. That's kind of like taking all of your module level attributes and putting them in a class. So now you can have more than one of them, and you need to have reference to the class object, to the instance in order to be able to talk to those variables. So you can have multiples, and you could have multiple threads talking to individual objects, individual class objects, and they wouldn't stomp on each other. So that would get you a long ways. The real problem was reference counting, and his solution for that was he had a single lock which you had to acquire in order to change your reference count. So you had to acquire it, change the reference count, and then drop it very quickly. But people were constantly grabbing and releasing this lock so much that the lock itself caused a really big performance degradation. So as a result, Python was between 4 and 7 times slower. This is according to David Beasley, who revived this patch in 2011 to sort of experiment with it and report on how well it worked, which was to say not very well. A couple of years ago, Antoine Petrou did an experiment where he played with something called atomic, Incre, and decr. So modern CPUs have what they call these atomic instructions, atomic test and set, where it's a way of incrementing and decrementing a variable, a number out in memory somewhere, in such a way that it's guaranteed to be an atomic operation. You can't have erase because nobody else can see the changes until they've already happened, kind of like a database or something like that. So this atomic Incre and decr is supported by basically all the CPUs that Python cares about these days. Antoine's experiment, he didn't have to change the API in order for it to work, and he found that it was about 30% slower, which is not the 0% slower that Guido is demanding, so he kind of abandoned this approach. But it did work. Now, I will point out to you that CPython is not the only Python interpreter out there in the world. There are 4 that are pretty famous, that are pretty well used. Jython and IronPython and PyPy. And of those 4 interpreters, CPython is the only one that uses reference counting. Reference counting. The others use what's called garbage collection. And CPython is the only one that really has a GIL. The others, so PyPy kind of has a GIL. My understanding is it's used during garbage collection cycles. But Jython and IronPython don't have any GIL whatsoever. It's perfectly possible to have a working Python interpreter that doesn't have any sort of GIL. Works fine. It's just technically very demanding. And they're using what I would call pure garbage collection. So pure garbage collection is another approach to managing the lifetime of objects very quickly, instead of having this reference count where you know how many people are holding a reference to it. Instead, every so often you sort of, the easy way is to stop the world, stop all computation, and examine all of your structures in memory, all of your objects, and all the ones that you can't, all the ones that aren't live, all the ones that aren't connected to your program running right now, you say, okay, that's not in use anymore, and you collect it. So pure garbage collection would work in Python, obviously, but it would require massive API changes, and it would break every C extension out there. And I cannot understate how important it is to not break all of the C extensions. C extensions are a very important part of the lifeblood of CPython. We break all the C extensions, it's kind of like starting over. I mean, Python 3 broke all of the C extensions, and look how slow Python 3 adoption has been. Would it be slower or faster than CPython with reference counting? It's hard to say. We wouldn't really know until we did it. Conventional wisdom about garbage collection is that it's about the same speed of reference counting, so I'm hopeful that it would at least be fast enough. But I think that breaking all the C extensions out there is something they can't really afford to do. But something else to consider, again, Python is the only one that doesn't have pure garbage collection, but Python is also the only one that has a C API. It's interesting to consider that all the modern languages, all the modern virtual machines don't have C APIs. They don't allow you to poke at the running interpreter the way the CPython does. If you want to write an extension, instead you write it from inside of the language and you use something like C-types or CFFI, because you might want to change how the garbage collector works. During PyPy's lifetime, it started out with simple garbage collection, and then it added incremental garbage collection, and then it added generational garbage collection, or maybe I got those in opposite order. But my point is that they've changed the garbage collection thing. Well, if you change garbage collection, you're changing how object lifetime works. And if you change how object lifetime works, that means changing the C API, because it's a very important part of that. You have to manage objects if you're going to be talking to the internals of the interpreter like that. So if they had a C API, PyPy would have broken it twice, like irrevocably broken it for everybody. And so I would suggest that if you have garbage collection, you kind of want to avoid having a C API anyway. And in fact, you kind of want to avoid having a C API just so that you don't have to expose your garbage collection or your reference counting to the world. So in my opinion, if we want to talk about getting rid of the GIL, exposing a C API to the world means exposing memory management to the world, and we've already done it, and we have we have reference counting. We can't afford to change it without breaking every C extension, which means that we can't afford to change it. And so the only thing we can do is something that doesn't change the C API. So I think atomic, Incre, and Decker is probably the only thing that would work. Thank you.
Sounds strange to me. Like, have anyone tried to do a ThreadLocal increment count for ref count? For example, just keep per thread the counter, and only when you get back to 0, maybe just reach out to find out if other threads have a different value for that.
You want to store the reference count of an object in ThreadLocal storage?
Yes.
So would there, if you had an object that was shared between threads, each thread would have its own reference count for the object?
Yes.
So then, if one thread, the reference count reaches 0, we release the object's memory, and the other thread is still holding?
No. If you reach down to 0, maybe you can have an external garbage collector to find out if all the values from all threads are 0, and then you release it.
Well, to answer your question, no, I don't think anybody has tried that experiment with CPython. There are various approaches people have proposed about moving the reference count out of the object and into some other storage somewhere. I think Mark Shannon, who skipped this because he's seen this talk before, he's talking about a way of sort of taking reference count changes and like just writing it down somewhere is kind of like a transaction log and only computing them in little bursts now and then. So instead of having to hold the GIL constantly and changing the reference counts constantly, you just do it as a sort of a batch processing step later, and you would free all the objects then. So there are ways to alter the reference count approach that you could get rid of the GIL and still preserve reference count and do something besides atomic Incre and Decker. I really have no idea how well they would work. I haven't read the research about this. Mark says, yeah, it could work, so I trust him.
Thank you.
Can I ask about what's your opinion on software transactional memory?
Yes.
That's quite interesting in terms of the deadlock situation.
Very interesting, yes. So there's a research branch of PyPy called PyPy-STM, Armin Rigo, who, when Armin Rigo walks into a room, he's the smartest man in the room. He's working on this. So software transactional memory is kind of like taking transactions, like database transactions, and using them for memory. So what it effectively means, like if you have a thread that's running and it says, I'm going to read this variable from memory, and I'm going to write this value to memory, and I'm going to write this value to memory, and now I say, commit the transaction. The rest of the world doesn't see any of these changes to memory until I have done the commit. So if you have two threads that are both doing work, they both might be committing, attempting to write to memory externally, and then they say commit. The changes don't actually happen out in the world until they say commit. And if two threads make commits that collide, then you roll it back, and you start over again, and you do it over again, just like databases. He's gotten this to kind of work. It's very complicated. So to answer your question, what do I think about it? I think it's very interesting. I think it's very complicated. One of the things that's really great about CPython is that it's very easy to work on. Internally, there's nothing that's terribly complicated. The code is very easy to read. It's very conceptually easy to understand because there's nothing terribly complicated going on inside. Whereas compare that with PyPy, it's bafflingly complicated internally. And then STM makes that way, way worse. So I talked to him about it. I said, would it be worthwhile? He actually wrote his STM support as two pieces. There's a C library called STM-GC7 or something like that, which means it's the 7th time he's started over from scratch, thrown away the old one, and started over with a blank piece of paper. He's working on 8 because he's doing it again. And then the PyPy variant uses that library. I said, would it be worth trying to port that library and use it from inside of CPython? And he said, don't do it. It is so complicated, it's so maddeningly difficult to get right that he's using like code generation in order to do it inside of PyPy, and he can't get it right from a code generation perspective. Expecting a C programmers, so I made the point that reference counting is simple, people still get it wrong. Expecting human programmers to get the PyPy STM interface correct is just simply, it's impossible. It's not going to happen. So CPython adopting STM, as long as STM is as complicated as it is, which I think is going to remain constant, I don't think that it's something that CPython should do.
Just one more comment on that. Except from being complicated, it might be as well more slower than the CAS solution that they had for atomics. Like,
no, that's the wonderful thing. Except if you do it
in hardware, but Intel failed to do that in hardware as well.
Well, we won't know until we try, but the theory about STM is that it really should be, it should have almost no overhead whatsoever. I mean, you need a lot of memory for this transaction log, and so that's adding a little bit of overhead for tracking that transaction log, but the actual overhead is very small, and so you're getting almost linear scaling when you're adding more cores, and as long as you have a reasonably parallelizable problem, that is. So STM, the whole point of it is that it doesn't add very much overhead and it doesn't slow down your program very much, but it's conceptually very difficult and it's conceptually very hard to get right. So those are really the major critiques of STM as far as I'm concerned. It's not that it would make it slower. It would be wonderfully performant. Any other hands raised? I think I'm keeping you from lunch.
Hi. You mentioned at the first slide about the atomic increment and decrement that it was 30% slower. Was that just because it was the first draft of the implementation? Because at the end you recommend this is probably a good way to go forward.
No, it's 30% slower because in order for atomic Incre and Decker to work, like it's the overhead of the atomicness as opposed to just being Incre and Decker. So making it an atomic Incre and Decker instead of just Incre and Decker, that's the thing that's 30% slower. I don't know that much about how modern CPUs work internally, but like modern CPUs have these enormous pipelines where it's doing all this work, you know, on the theory that it may work out in the future. And my guess is that an atomic Incre and Decker basically cause everybody to spill their pipelines and start over from scratch. And so you're throwing away prospective work that you're trying to do, and there's a little bit of synchronization internally. My guess is also that an atomic Incre and Decker maybe sort of stops the other cores on the CPU from running for just a split second. And again, that's going to be overhead, and that's going to slow you down. But again, this is all me making stuff up. I don't really know.
Now that we know more about the GIL and how it works and all its understandings, what do you recommend for new and old and Python developers alike for the best threading experience if you get your parallelism right? What do you recommend in your experience?
What do I recommend for who? I don't understand the question.
Like, you said there's different ways, there's different implementations of Python.
Right.
Does
Going forward, if you were starting today and you were going to write a new language today, what do I recommend you do?
Yeah.
Yeah. Oh, that's very clear. All of the new work that happens in dynamic languages is all using garbage collection, pure garbage collection. And I think that absolutely the way forward is you use pure garbage collection and you don't have a C API and you force people to write extension modules, quote unquote, in your native language using something like CFFI or C types where you're calling out from the language into the C thing. And that's what everybody's doing now. That's what Rust does. That's what Go does. Nobody has a C API, and they're all using garbage collection. And I'm not going to argue with those people because they're really smart.